All right, we are back. This is Techmath2. We're looking at, in the red book, we're on page 55. We're looking at number 148. That is 1.16. They want us to convert degrees to radians for the unit circle. And again, if you're kind of a visual person, this would probably make sense. Remember how we convert. We do 45 degrees. It's pi radians, 180 degrees. And so that's going to end up with the degrees canceling. And so we have 45 pi over 180 radians, and we can definitely reduce that. 45 divided by 45, and that is pi over 4. So pi over 4 radians, which does make sense. That's 1/4 of 180 degrees, or 1/8 of 360 degrees if you cut it into 8 equal pieces going around the circle. 1/8. I think that's what they did. Visually, they said, oh, look, it's 1/8 of 2 pi, and then reduced the 2 and the 8 to be pi over 4. So, okay, let's get into, let's pretend for a moment that you didn't have a calculator. Oh no, no calculator. The very basic structure of right triangles, there's two kind of famous right triangles, 45, 45, 90, and 30, 60, 90 triangles. So first let's examine a 45, 45, 90. This is 117. So if I have a right triangle, and I know that's 90 degrees. And I know this is 45 degrees. If that's 45 degrees, then this also has to be 45 because interior angles of any triangle have to add up to 180. If this is 90, 90 plus 45 is 135, and then 180 minus 135, because they always have to add up to 180, is 45. So we have a 45, 45, 90. That's also, if those angles are equal, then the sides opposite have to be equal. So see how it opens up. So look, we'll call this 1. If that's 1, then that side would also have to be 1, because they're both 45 degree angles. Think about how angles work. If I open this up, if this is 45 degrees, that distance is 1. If I made it 90 degrees, that distance would be more. If I made it 130 degrees, that distance would be more. And so if this angle is 45 and I replicated it, made another angle that was 45 with the same radius, then that distance, the opposite distance would always be the same. So even if this wasn't 1, if this was 5 and 5, it would have to be both 5s. If this was 21 and 21, if it's 45, 45, 90, it's an isosceles triangle. Two of the sides, opposite angles, have opposite sides that are the same size, all right? So now if we apply Pythagorean's theorem to it, remember Pythagorean's theorem, a squared plus b squared equals c squared? I can find the hypotenuse. 1 squared plus 1 squared is equal to c squared. 1 plus 1 equal to 2 is c squared, so c is equal to the square root of 2. So every 45, 45, 90 has a ratio of 1, 1 in the square root of 2. If it was 5, 5, then it would be 5 square roots of 2. If it was 12, 12, then it would be 12 square roots of 2. But it's always going to reduce to this ratio, 1, 1 in the square root of 2. All right? So even if I had a bigger right triangle, way bigger, and we'll say this was 12.5 and 12.5, because it's 45, 45, 90, then I know this would be 12.5 square roots of 2. All right? So it's always those ratios work. And then if I reduced it down, I shrunk it down to 1, it would go 1, 1 square root of 2. All right? So keeping that in mind, now, with any 45, 45, 90, if we know it's a 45, 45, 90, and we have at least one side, so we have a reference point, we could figure out the sine, the cosine, and the tangent without our calculators, basically. So let's do a couple. Look at 152. We've got 135 degrees. If that is 135 degrees from there to there, then we know this is a 45-degree angle. If that's 45, that's 90, this is 45. So we have a 45, 45, 90. So if they want the cosine of 135, let's blow this up into a triangle that's easier to see. And see what we have here. We have 45, 45. And let's see that we need at least one other piece of information. They told us using the values from the last frame, find the cosine. Do you get one? So they want the tangent of 135 and the cosine of 135. And we do know that the radius, what do we know? We found the sine, cosine, and tangent of 45 degrees. So they did give us the 1 and the 1 and the square root of 2. So basically the radius was the square root of 2. That was given. Okay, so now look, we go like this. So you say, okay, the cosine of 135 degrees. Remember what cosine is. Cosine is adjacent over hypotenuse. 1 over the square root of 2. But let's put it in the context of this picture. Okay, so this is the big picture. That's just a standalone triangle with sides 1, 1, and the square root of 2. But in context of the coordinate plane system, this point on the graph is -1. That x is negative. That's positive, and r is always positive. So the only time you add a negative is if it's x or y. If it was down here, they both would have been negative. It would have been negative, negative. All right? So it's -1 over the square root of 2. And I believe this book accepts that. In some of the answers, in the answer key, they leave it like that. If you had an algebra class, this was a big no-no for us algebra teachers, really get bunged about that. We make you rationalize the denominator. So you can do that, but you don't have to in this course. That means you multiply it by itself on the bottom. You get negative square root of 2 on the top, -1 times square root of 2, negative square root of 2. On the bottom, you get the square root of 4. It's called rationalizing the denominator because basically you got rid of the square root. So it's negative square root of 2 over 2. It's actually what they have in your book, but I got to tell you, in the homework and the answer sheets and things like that, they'll often just leave it like this. They don't care. They'll leave the square root on the bottom instead of fixing it so there's not a square root on the bottom. Again, this is a big algebra thing that we really push that in algebra to rationalize the denominator because they're trying to prep you for calculus. When you're doing calc, it's really hard to differentiate and do integrals if there's a square root in the denominator. So you don't actually use rationalizing the denominator in algebra, but that's usually where you learn it in the progression. Okay, they also want us to find tangent. Well, tangent will be a little easier here. 135 degrees. That's -1, so tangent is opposite over adjacent. So 1 over -1, which is just -1. So that's a lot easier. Okay, let's look at 118. 30, 60, 90 triangles are also rather interesting. And so this one has a kind of cool little thing on it too. So 45, 45, 90 was because it was an isosceles and 90 degrees. If it's isosceles, meaning two sides are the same, two angles are the same, and it has to be a 45, 45, 90. The 30, 60, 90, you might be like, where did that come from? Well, this is where that came from. If you have an equilateral triangle, meaning all the sides are the same. So let's pretend we have this equilateral triangle, all sides 2. It'll make sense why I picked 2 in a second. Equilateral triangles, all 3 sides the same, are also equal angular triangles, which means if all the sides are the same, all the angles have to be the same. If all the angles are the same and they have to add up to 180, Well, then 180 split into 3 even pieces is 60 degrees. So we have 60 degrees here, 60 degrees there, 60 degrees there. Okay? Now here comes the weird part. I'm going to take and drop an altitude, meaning a 90-degree line that's going to plop right there. That is now 30 and 30. It was 60 degrees, but I split it. I bisected it, so it's 30 degrees. I also cut that in half, so it's 1 and 1. Now let's just take this part. So we have 2, we have 1, we have our brain and the Pythagorean's theorem, so we can find this length. We know this is 30 degrees. We know this is 60 degrees. Okay? And so 30, 60, 90 triangle. Pythagorean's theorem says a squared plus b squared is equal to c squared. So 1 plus b squared is equal to 4. Isolate the variable, so we subtract 1 from both sides. B squared is equal to 3. Take the square root. It's plus or minus, but since it's a length, it's only plus. So the square root of 3. These are always true. The side opposite the 30 is always 1. The side opposite the 90 is always 2. And the side opposite the 60 is always the square root of 3. So now again, what if I have a big 30, 60, 90 triangle, okay, where this is 90, this is 60, and this is 30. And let's say I know that this side is 15. All right, we're going to use these same ratios. If this side is 15, this side, the hypotenuse, is 30. Because this side was 1 and that side was double 1, which is 2. So double 15 is 30. Square root of 3, 15 square roots of 3. Because that's 1 square roots of 3, basically. All right? So no matter what side they give you, if they give you any one of the sides, you can find the other two with a 30, 60, 90 triangle. And it's all kind of based on this equilateral triangle and going from there. So let me erase this and give you another suppose. What if instead of that, I gave you this side was 70? If you knew the hypotenuse was 70 on a 30, 60, 90, well then you know the side opposite the 30 is always half of that. So it's 35. And then the side opposite the 60 is always whatever this side is times the square root of 3. And so no matter what, if you have one side of a 30, 60, 90, you have all three sides. Okay? Same as if you have one side of a 45, 45, 90, you have all three sides. It's always the same ratio. So let's take a look at how they play along with this. They did a 30, 60, 90, 1, 2, and the square root. Okay, we did that already, so we don't have to do that one. Let's do 158. So 158, they want me to find the cosine of 150. And they want me to find the tangent of 150. And that's given, we know the 30, 60, 90 triangle. So this is 150. If that is 150 degrees, then this guy is 30 degrees. This guy is 60 degrees. And so what do we know about this? Well, we know the hypotenuse is 2. We know that the side opposite the 30 is always half of that, so that's 1. And the side opposite the 60 is the square root of 3 times this, so 1 square root of 3, or just the square root of 3. Now, in the context of the coordinate plane system, this coordinate right here is negative square root of 3, comma, 0. This coordinate right here is negative square root of 3, comma, 1, and that's 2. So because of where it is, I know lengths can't be negative, but we'll just put the negative on there as to notate where it is on the coordinate plane. All right? And so then, if you want the cosine of 150, the exact cosine of 150 degrees, Cosine is adjacent over hypotenuse, so it's negative square root of 3 over 2. If you want the tangent of 150, that is opposite over adjacent, so 1 over negative square root of 3. And then, again, they fixed it this time. Often they don't. Like I said, in like the answer keys and the reviews and things, they let you just leave it like that. But if you rationalize the denominator, you're multiplying top and bottom by the square root of 3. And you get the square root of 3 over negative square root of 9, which is just negative square root of 3 over regular 3. No square root on it. But, and I want to stress this, if you leave it like this, it's also fine for this course. This is like a big algebra thing. You're okay to leave it like this if you want. All right? Okay. That is about it for 118.